That bus fellow is again calling me. Hello. Oh, it's fine. Is it time? Is it the time to start? Is it?
A very good morning to one and all. On behalf of the Center for Advanced Research in Applied Mathematics and Statistics, CARMS, and Manipal Academy of Higher Education, it is my privilege to welcome you all to the inaugural ceremony of the International Conference of Linear Algebra and its Applications, ICLAA 2025, being held from December 17 to 20th, 2025, here in Mahe, Manipal. May I now request the convener and organizing secretary of ICLAA 2025 to kindly escort the dignitaries to the dais.
Please, okay. Other side is easier.
Okay, yeah, easier for me.
At least when go. Yeah, please follow the view and then go. Or you want later we'll light the lamp and. We're going to take the laptop and get him downstairs.
I will take your help.
Trouble for me. Very well. Okay, start here. Start here. Here.
1, 2, 3, कितना नहीं आता मुझे? 3, okay. This 3.
Yeah, sir.
Yeah.
Steve. Yeah.
To seek divine blessings for this event, I invite Miss Lavanya S., MIT Manipal, for the invocation. ಶರಣು ನಿನಗೆ ಶರಣು ವಿನಾಯಕ ವಿನಾಯಕ ವಿದ್ಯಾದಾಯಕ ದೇವ ವಿನಾಯಕ ವಿದ್ಯಾದಾಯಕ ದೇವ ಶರಣು ನಿನಗೆ ಶರಣು ವಿನಾಯಕ ಶರಣು ನಿನಗೆ ಶರಣು ಪಾಶಾಂಕುಶಧರ ಮೂಷಿಕ ವಾಹನ ಸರ್ಪಾಲಂಕೃತನೇ ಗಜಾನನ ಆದಿಪೂಜಿತ ನೀನು ವೇದ ವಂದಿತ ನೀನು ಮೋದಕ ಪ್ರಿಯ ನೀನು ಗಣಾಧಿಪ ಶರಣು ನಿನಗೆ ಶರಣು ವಿನಾಯಕ ಶರಣು ನಿನಗೆ ಶರಣು. Thank you, Lavanya. I now invite Dr. K. Manjunatha Prasad, Coordinator, CARMS, to deliver the welcome address.
Good morning, everyone. On behalf of the organizing committee, it gives me immense pleasure to welcome you all to the International Conference on Linear Algebra and its Application, ICLAA 2025. The journey of ICLAA commenced with the CMTGM 2012 and progressed through distinguished conferences held in Manipal in 2014, 17, 21, and 23, culminating in ICLAA 2025 now, which convenes eminent mathematicians, statisticians, and applied scientists worldwide to engage in scholarly discourse advanced research in linear algebra and foster innovation. The present conference, ICLA 2025, it is the sixth in its sequel, shall provide a platform for leading mathematicians and statisticians working around the globe in the theme area to discuss several research issues and to introduce new innovations. The main goal of the conference is to bring experts, young researchers, and students together to present recent developments in this dynamic and important field. A week prior to this particular conference, the Center for Advanced Research in Applied Mathematics and Statistics, MAHE, conducted international workshop on special matrices, graph, and applications, December 10 to 16, 2025, engaging eminent resource persons and participants. For ICLA 2025, the conference proudly features more than 150 distinguished, more than 30 distinguished invited lectures by leading experts, along with about 150 contributory, 120 contributory presentations. As part of this esteemed conference series, we have proudly published high impact proceedings, special issues, books, and volumes with renowned publishers such as Manipal University Press, Springer, Taylor and Francis, and others, showcasing exceptional research from distinguished contributors. Today, we have several dignitaries on the dais and off dais, and we have with us distinguished Professor S.K. Jain, Ohio University, Emeritus and Distinguished Adjunct Professor at King Abdulaziz University, a leading authority in applied linear algebra, non-commutative rings, and modules. He is an executive editor of Journal of Algebra and its Applications, World Scientific Press, and that the Bulletin of Mathematical Sciences, Springer Verlag. He is also serving on editorial board of Electronics Journal of Algebra. It is our privilege to welcome him to ICLA 2025. Now I request Dr. Kiran Varghese, Director PSPS, to welcome him. Thank you, Doctor. We are profoundly honored today to welcome Lieutenant General Dr. M.D. Venkatesh, leading the Manipal Academy of Higher Education, an institution of eminence and a deemed university, as a Vice Chancellor. He is a highly regarded proponent of health science, engineering, humanity, arts, and sciences. His leadership has been a driving force in the institution's pursuit of excellence in higher education. It is my privilege to welcome him to ICLA 2025. Now I request Professor Stephen Kirkland, University of Manitoba, Canada, to welcome him.
You did a good job.
Please. Yes, sir. Professor Kirkland, he is not here as a guest. He is a in-house person. He is a part of our scientific advisory committee.
You did a very good job.
Dr. Stephen J. Kirkland, Professor of Mathematics and Associate Dean at the University of Manitoba, Canada, and he is also a member of a Scientific Advisory Committee. Professor Baffert, who is the chairman of this particular Scientific Advisory Committee, is not here around because of his poor health. So I am requesting Professor Kirkland to take care of his position and take care of entire conference. He's an eminent scholar in non-negative matrices, combinatorial matrix theory, and spectral graph theory. It is my privilege to welcome him to ICLA 2025. We are privileged to welcome Dr. Cherin Varghese, Director of Prasanna School of Public Health at Manipal Academy of Higher Education with us today. I request Professor Harikrishnan PK to welcome. Our heartfelt welcome goes to all delegates, speakers, heads of institutions, department heads, faculty members, and participants whose presence promises an inspiring conference. Welcome, one and all. Thank you. I did not take eminent speakers who are here because I wanted to save my time. And our VC is here with he has a busy schedule. In spite of that, he is here with us, and he may have to go a little early, so he'll be addressing us a little in advance. And I thank him for taking the.
Thank you, sir. We extend a warm welcome to you as well. Deepa Jyoti Param Jnanam, the lamp's light is supreme knowledge. May I request the dignitaries to kindly proceed with the lighting of the ceremonial lamp, marking the formal inauguration of ICLA 2025.
Okay.
Yeah.
Sure.
Camper. We take the trouble of down and
Down and up.
roast to our founder.
No, I can. Yeah. Thank you.
Take your time.
I suppose you move a shoe.
Okay.
Now, may I request our esteemed dignitaries to kindly release the souvenir of ICLA conference. Thank you, dignitaries.
Electronic copy of this is available in our website. Please download it.
I now invite Dr. Vinay Madhusudanan, MIT Mahe Manipal, to kindly introduce our Honorable Vice Chancellor.
It is my pleasure, my honor to introduce to you Lieutenant General Dr. M.D. Venkatesh, the president of this inauguration session. Graduating with distinction from Mysore Medical College in 1978, Dr. Venkatesh was commissioned into the Army Medical Corps in 1979. He completed his MS ENT from Mumbai University in 1986 and is widely recognized as an accomplished ENT surgeon. He has received specialized training in cochlear implantation and neurotology, both in the country and abroad, and is an expert in his field. As a founding member of the Department of Medical Technology at AFMC, he made significant contributions to the field of medical education and trained several generations of students at AFMC Pune. He has held all academic positions from reader to dean of the prestigious Armed Forces Medical College, Pune, as well as several important administrative positions. He has also served as an assessor for the Medical Council of India, the National Board of Examinations, and the National Assessment and Accreditation Council. In addition, Dr. Venkatesh is advisor to DRDO on indigenous cochlear implant programs and is the chief clinical coordinator for clinical trials of indigenous cochlear implant programs approved by the Drug Controller General of India. He has been honored with numerous awards for his outstanding contributions to medical science, such as 2 commendations from the Chief of Army Staff and the Vishisht Seva Medal from the President of India. Dr. Venkatesh is a highly accomplished researcher of repute in the field of otolaryngology and medical education. He served as a governor of the Board of Governors for the Indian Academy of Otolaryngology and Head and Neck Surgery. After his 38 years of distinguished service at AFMC, he assumed the position of Vice Chancellor at Sikkim Manipal University. At present, he is leading the Manipal Academy of Higher Education as Vice Chancellor. So, as mentioned, he is a highly regarded proponent of health science, engineering, humanities, arts, and sciences, and has a strong commitment to recruiting and retaining top-tier faculty members. He has strengthened international partnerships, increased the number of endowed chairs and graduate fellowships, and prioritized providing researchers with essential resources to make significant contributions in their respective fields. His leadership has been a driving force in the institution in the pursuit of excellence in higher education. I invite Dr. Venkatesh to deliver the presidential address.
Thank you very much. Very good morning to all of you and warm greetings to everyone present here today from Manipal Academy of Higher Education, an institution of eminence deemed to be university. Dignitaries on the dais, dignitaries of the dais, eminent scholars, researchers, faculty, PhD scholars, and students. Finding a little out of place here from a medical scientist or a medical professional speaking in a conference which is dedicated to a very, very niche area of mathematics. But all of us know that mathematics is the mother of all sciences, and it continues to be even today. The importance given to mathematics in the context of Indian knowledge systems, culture, astronomy, astrology, and various other forms of science is something which needs to be recollected at this particular time. I'm very happy to be present here today, especially happy that Center for Advanced Research in Applied Mathematics and Statistics, established in the year 2018 at Mahe, with objectives of fostering advanced research and training in the area of mathematics, statistics, and their applications. It facilitates and bridges the gap between mathematicians, statisticians, and applied mathematicians working in the area of health, technology, and social sciences. Last 7 years of its existence, CARMS has been doing an extraordinary job and carried out multiple conferences in niche areas of mathematics and its applications. Today,
today's conference is on linear algebra and its applications. To us at Manipal Academy of Higher Education, where multidisciplinary education and multidisciplinary research is the mantra for success. As we look at it, if you look at the applications of linear algebra as a fundamental discipline, there are vast applications across science, engineering, technology. In this current research ecosystem and space across the world, multidisciplinarity and transdisciplinary research is the way forward for the entire world to move ahead. And in this particular direction, linear algebra's role cannot be overemphasized. It cuts across disciplines with applications in data science, machine learning algorithms, computer science and graphics, image processing, computer vision, and search engine ranking. Some of the applications in science, technology, and computer sciences. In physics and engineering, perhaps it has the greatest application in quantum sciences, quantum mechanics. And as the world moving towards, I was hearing to some of the leading, proponents of science and research, the next 10 years, the world is moving in a different directions with emphasis on scalable quantum technology, in digital superintelligence, and precision medicine. In all these three areas, I personally feel that linear algebra and its applications are going to make a huge impact in terms of modeling, in terms of projections, and in terms of predictions. So it's a precise science, and I think today we cannot do without linear algebra and its applications in any field. Particularly happy that the Prasanna School of Public Health is also part of this organizing team. It's got a very strong data sciences department, bioinformatics department. There are various other departments and institutions in MAHE which are doing pioneering work in bioinformatics, data sciences, statistics, bringing in different researchers from across disciplines into one forum and ensuring that cutting-edge research happens for the benefit, not necessarily bringing in reputation to the researchers and the institution, but to the entire globe as a whole. The other applications of linear algebra cannot be overemphasized in cryptography, finance and economics, especially in economic modeling. It's got a huge impact. And of course, I stressed on the importance of linear algebra and its applications in bioinformatics and statistics. It's very heartening to see that we have almost 15 international speakers who are going to be addressing these very niche areas and conducting plenary sessions. And we have almost 18 Indian eminent researchers in this field who are going to be speaking to the conference. And we have almost 140 total contributory talks in this very niche area. Department of Mathematics at MIT Manipal is doing an extraordinary job. Perhaps the strongest basic sciences department in the university. It's fostering great learning culture, interdisciplinarity, and of course, pure research in the field of mathematics and its applications. Let me congratulate the Department of Mathematics on this extraordinary work. And something very important I would like to stress. The Department of Mathematics is spearheading one of the niche programs, which is a Bachelor of Technology in Mathematics and Computing. Very unusual that a basic sciences department is spearheading and driving a technology-based bachelor's program. Congratulations for conceiving and continuing this. So on this very happy occasion, extremely happy to be here today. I feel privileged to be invited to this exceptional conference. I wish the conference all the success, and I'm sure the deliberations will lead the way to multiple collaborations, networking, newer research ideas, and newer applications of linear algebra in its current form and in its futuristic note. Future has to be linked with the progress in mathematics, and I'm sure this conference is going to bridge that gap to a great extent. I wish this conference all the success. I wish all the delegates great academic fees and also enjoy a wonderful academic atmosphere at Mahe and go around, look around. It's just not about technology. Literally every discipline is represented on this campus, which is currently housing close to 30,000 students, 3,000 faculty, 15,000 teaching and non-teaching staff, 150 research centers, 10 university departments, and 29 university institutions. The scale and the magnitude is extraordinary, but I'm extremely pleased that there is a highest level of collaboration between disciplines, be it be science technology, be it be health sciences, be it be social sciences, humanities, management. So I wish this collaborations continue and we grow together, we foster together, and we succeed together. Wishing this conference all the success. Thank you very much and Jai Hind.
Thank you, sir, for those inspiring and valuable insights. Due to pre-scheduled commitments, our esteemed vice. I now request Dr. Varun S.G., Department of Applied Statistics and Data Science, Mahe, Manipal, to kindly introduce Dr. Stephen J. Kirkland from Scientific Advisory Committee.
Thank you for being here. I apologize to everybody. I have a prearranged commitment which I need to be there at 11 o'clock. Thank you. Some of it is excellent, but I'll give it to you.
Due to pre-scheduled commitments, our esteemed Vice Chancellor will be taking your leave shortly. We sincerely thank him for gracing this occasion with his presence.
Yeah, be there.
Good morning, everyone. It's my pleasure to introduce Professor Kirkland to this August gathering. So, Dr. Stephen J. Kirkland is a professor in the Department of Mathematics and Associate Dean of Faculty of Graduate and Postdoctoral Studies at the University of Manitoba, Canada. He earned his PhD from the University of Toronto in 1989. His research focused on theory and applications of non-negative matrices, combinatorial matrix theory, and spectral graph theory. With over 160 journal articles and 5 books, he is editor-in-chief of Linear and Multilinear Algebra since 2006. A fellow of the Canadian Mathematical Society and former president of the International Linear Algebra Society from 2008 to 2014. He serves on multiple editorial boards and scientific committees. Please join me in welcoming Dr. Stephen J. Kirkland. Over to you, sir.
Thank you, and good morning to everybody. So yesterday, the tea break at the workshop, Professor Prasad came over and said, well, Ravi Bapat's not here, so you're going to take his place. So I'm going to make no uncertain terms about this. I cannot take the place of Ravi Bapat. Nobody can. They're massive shoes to fill, especially at this setting here. I think we can agree that he's the beating heart of the ICLAA, and we wish him all the best, even though he's not here. So I was asked to give an overview of the series of meetings, and so it's I looked into the history. ICLAA has a solid history with a prototype meeting in 2012, the International Workshop on Combinatorial Matrix Theory and Generalized Inverses, which was the sort of the genesis of the sequence of international conferences on linear algebra and its applications held in 2014, 2017, 2021, 2023, and now 2025. I'll note that Iclaa does not operate in a vacuum. So the Center for Advanced Research in Applied Mathematics and Statistics, CARMS, produces other linear algebra events, including workshops on applied linear algebra, probability, and statistics in 2004 and 2025, computational linear algebra and graph theory using SageMath in 2024, workshops on special matrices, graphs, and applications in 2023 and 2025, and many, many others. I'll just say, from my view as a former president of the International Linear Algebra Society, I really want to commend CARMS for its support for linear algebra and its allied areas. To me, it's no coincidence that the growth of linear algebra in India has accelerated precisely during the period in which CARMS has been so actively supporting our discipline. So kudos to CARMS. Our current meeting, Iclaa 2025, has almost 200 participants and more than 30 invited speakers, and promises to be an exciting event that will feature the latest developments in linear algebra and its many, many applications, some of which we heard earlier. Iclaa has grown in size, scope, and strength over the years, and it's gratifying to see more and more young researchers involved in this sequence of meetings. In particular, one of the things that I've observed in my participation in the sequence of meetings is maybe 10 years ago, people who were early career or junior researchers were giving talks. Well, you know what? Those same people are now the invited speakers in this year's program, and they have their own research teams that they brought with them to participate in this meeting. To me, that's a sign of a very healthy scientific community working linear algebra in this country. So I'll just close up with a thanks to CARMS, and especially to Professor Prasad, who's had the leadership for organizing the next chapter in this exciting sequence of meetings in linear algebra. Thank you.
Thank you, sir, for your insightful and enriching overview of Iclaa 2025. I now request Dr. Sachin, MIT Mahe Manipal, to kindly introduce our chief guest, Dr. Surinder Kumar Jain.
Good morning, everyone. It is our honor to introduce our esteemed chief guest, Dr. Surinder Kumar Jain, Emeritus Professor at Ohio University and renowned expert in linear algebra and non-commutative rings. Dr. Jain has authored more than 135 research articles that have been published in professional journals. He has co-authored 5 influential undergraduate and graduate texts, including the widely acclaimed Basic Abstract Algebra, Linear Algebra and Interactive Approach, Topics in Applied Abstract Algebra, and Cyclic Modules and Structures of Rings. He serves as an executive editor for the Journal of Algebra and its Applications and Bulletin of Mathematical Societies, and on the editorial board of Electronic Journal of Algebra. He has supervised 23 PhD dissertations in non-commutative rings, modules, and applied linear algebra, and holds lifelong membership in the Indian Mathematical Society alongside membership in the American Mathematical Society. With great pleasure, I invite our chief guest, Dr. Surinder Kumar Jain, to address the gathering.
Well, it's my great pleasure and privilege to be here. I know, Dr. Prasad, you won't believe, since 1980 and even before.
No, 1990.
90, okay. So that has been so long. We have been co-workers, published research papers together, taught so many things. He is a great, not only mathematician, as a great human being. He has established this series of our linear algebra conferences, which has proved a great success, not only in India, but people talk about it all over the country and all over the world. This is the 6th one, and I have been attending each and every one. I listen to all these invited talks and learn a lot in this process. The most beautiful thing about this is that I see many more young workers than in any other conferences I go to. This is really a positive sign for the development of the subject and of this kind of discipline. This is it has not, let me be honestly saying, linear algebra may not be looked upon by the mathematicians at the higher level as one of the hot ones. But it is indeed a very valuable, hot subject. It is valuable as the Vice Chancellor who just left. I say you should listen to his talk over and over again, what he said. I was very impressed the value of this linear algebra is in almost all disciplines, including medical sciences. My family has a lot of medical doctors, my son and others. And in fact, my son loved linear algebra when he was a student. So I'm just telling you, this is a great opportunity for all who come here and attend and listen to the conferences. I can name several people who come here, but the list goes on and on. I'm not going to name one, and so they leave somebody else. It will not be a good idea. Well, what I was going to say further, who is the one who is doing all that? This is Prashad, my old friend. He has dedication, discipline, and most important, his ability is great contribution to research in mathematics. And that is what I greatly admire about him. Not only he is a researcher or a mathematician, but he is also organizer. I have not seen a single speck of weakness in any place, whether it's a living where accommodation is provided, or it is a food, or it is arrangement for picking up. I find everything is great. So I greatly thank him. I thank the administration for helping him, the Vice Chancellor, the Director, and others whose deans who are going to provide all the support for this conference. I have no more words to say, but I'm very much grateful to all of the people here who organized this thing, the administration, the dean, the Vice Chancellor, and I wish that this continue for a longer time, for all the time to come. Thank you very much.
Thank you, sir, for your enlightening and gracious address. I now invite Dr. Srinath Hadimani, MIT Mahe Manipal, to introduce Dr. Cherian Varghese, Director, Prasanna School of Public Health.
Good morning, everyone. It is my honor to introduce our distinguished guest, Dr. Cherian Varghese, Professor of Global Public Health Policy and Governance and Director of Prasanna School of Public Health at Mahe Manipal, India. Dr. Varghese has extensive experience with World Health Organization, where he has worked on non-communicable disease programs and public health initiatives. He has authored over 100 publications in field of NCDs and hold advanced degree in epidemiology from Cambridge, UK and Tampere, Finland, along with medical qualifications from India. It is my pleasure to invite Dr. Cherian Varghese to address the gathering. Please, sir.
Thank you for the kind words. Respected Vice Chancellor Dr. M.D. Venkatesh, Chief Guests Dr. Stephen J. Kirkland and Dr. Surendra Kumar Jain, esteemed resource persons, participants, faculty, students, ladies and gentlemen. As we have heard, this is a unique conference and the School of Public Health is pleased to co-organize this conference along with the Center for Advanced Research in Applied Mathematics and Statistics. As we heard from Dr. Prasad, it is a series, it is like a Netflix series, it is just continuing and continuing, which is really good because then only you can, once in a while, it is not going to help. It has to be a continuous process. I am also from the medical field, but I have a bit of epidemiology experience and disease modeling, and I always think that linear algebra, as I understand, is the mathematics of data. Okay, so the mathematics of data has to be there for the data to really perform well. And it is crucial for public health modeling, disease spread, optimizing resource allocation. And disease modeling is something that we really have to look at in the current scenario. We had COVID and I was in WHO at that time. We were every day doing different scenarios, an optimistic scenario, what will happen, a pessimistic scenario, what will happen. So all this needs your fundamental work in linear algebra because then only all these things will work out. The other major area is genomic risk assessment. I'm sure within 3-4 years, you pay $20 to a lab on the roadside, they will give you a full genomic thing and say, okay, these are the abnormalities. So what do we do with that? You have to have real good algorithms to take you through the next step. Who will create that algorithm? It will be the work of all of you sitting here. So there is no end to it, whether it is diagnostics, outbreak prediction. So within the field of public health and medicine itself, there's a huge application for linear algebra and the related products. Also, as we heard, gone are the days when education was just compartmentalized into humanities, mathematics, and biological sciences. That is not going to apply anymore. I think the current understanding, you should have a full 360-degree view of the whole thing that you're studying. Just because you're doing the linear algebra or mathematics does not mean that you should not have any idea about what is public health or what is humanities. And similarly, the other way also. And I'm sure in the next few years, education is going to change drastically from the traditional rote approach of putting science and humanities into separate buckets. And I'm sure this is a good start. And again, I'm impressed by the number of youngsters who are here who will really give a hope that these are areas that we can really make a big advance. I just want to have a special appreciation for my colleague, Dr. Manjunath Prasad, coordinator of CARMS, for his leadership and guidance and quiet and sincere work to make this happen. Thanks to Dr. Arun, whom you have seen has suffered a major accident, but even then he has put up a brave face and has helped us to take us through. The MIT departments and various other departments coordinating this have really done great work to make this happen, because these things just does not happen overnight like that. Somebody has to put in a lot of effort. So let me thank everyone and wish you all a successful conference and productive collaborations. Thank you very much.
Thank you, sir, for your profound and inspiring address. To conclude this inaugural ceremony on a formal note, I invite Dr. Harikrishnan PK, Organizing Secretary, ICLAA, to propose the vote of thanks.
Good morning to all. On behalf of the organizing committee, it is my great pleasure to propose the vote of thanks to this August gathering. It is my privilege to express our heartfelt gratitude to the chief guest, Dr. S.K. Jain, Ohio University, USA, for his gracious presence and inspiring words, which have been a great source of encouragement to all of us. Thank you, sir. We gratefully acknowledge the wholehearted support of the president of today's program, our Honorable Vice Chancellor and General Dr. M.D. Venkatesh, sir, for his valuable guidance, advice, and constant encouragement for the successful conduct of this conference. Thank you very much, sir. We take this opportunity to extend our sincere thanks to Dr. Stephen Kirkland for providing a comprehensive overview of ICLA 2025. Thank you, sir. Our sincere thanks are also due to Dr. Cherian Varghese, Dr. PSPH, for his insightful advice and continued encouragement towards his conference. Thank you, sir. We express our gratitude to Dr. Anil Rana, Director MIT, and Dr. Chandrakala, Joint Director MIT, for their constant encouragement and valuable support. We express our gratitude to Dr. Kunjam Shyamprasad, Head of the Department of Mathematics, MIT, and Dr. Asha Kamath, Head of the Department of Applied Statistics and Data Science, PSPH, for their support and cooperation. We extend our warm regards to and sincere appreciation to all the plenary and invited speakers. I am not listing the names. Some people are yet to arrive and some people are here. Sometimes I may miss some names. For accepting our invitation to enrich us with their talks on different disciplines in this conference. So we thank the government funding agency DST ANRF now, for their partial support for conducting this conference. Our special thanks to all delegates who are attending this conference offline and online mode. Online means some speakers are due to some problem, they are attending online, from various universities from India and abroad, and teaching faculties present here. We thank Mahe and MIT for providing the logistic support to organize this event. We thank the HOD of Civil Department in charge of KEF R&D Center, this conference building, and the caretaker, Mr. Durga Prasad, for their support to conduct this event here. A note of thanks to the staff, security officials of MIT, and especially to Mr. Manu for capturing this meeting. Thank you all for their presence and support. Have a great day. Thank you.
Thank you, sir. We now request all the participants to proceed to the ground floor for high tea. The technical sessions will begin shortly after the tea break. Thank you. Participants, please note, during the tea break, there will also be group photo session. Please join with us. Thank you.
Next, all invited talk are here. Next question is carried by the next Oh, I'm winding up now. I mean, 2 words for four.
There must be something that's really fun. Yeah, so I think that basically here, that's where. And these guys.
Had I been little longer, I would have taken our help kind of.
The problem is the following, no, that you see, younger people don't want to spend much time on.
I know, but
ಮತ್ತೆ ಕ್ಯಾಮರಾ ಅವಶ್ಯಕತೆ ಇಲ್ವಾ? ಕ್ಯಾಮರಾ ಬೇರೆ ಅಕೌಂಟ್ ಮಾಡ್ಬೇಕು. ಹಾ ಹೌದು. ಅಲ್ಲ ನಾ ಸಪ್ರೇಟ್ ನನ್ನ ಲ್ಯಾಪ್ಟಾಪ್ ಕನೆಕ್ಟ್ ಮಾಡಿರ್ತೇವೆ ಕ್ಯಾಮರಾನ ಅಲ್ಲಿಂದ ಸ್ಟ್ರೀಮ್ ಮಾಡ್ತಿದ್ದೆ. ಹೌದು ಅದಕ್ಕೋಸ್ಕರ. ಬೇರೆ ಬೇರೆ ಯಾವ್ದಾದ್ರು ಮಾಡ್ಬೋದಾ? ಅಲ್ಲ ಅದರಲ್ಲಿ ಇವ್ರಿಗೆ ತೋರಿಸ್ಬೇಕಲ್ವಾ, ಬೇರೆ ಜನರಿಗೆ ಅಬ್ರಾಹಂ ವರ್ಮನ್ ತೋರ್ಬೇಕಲ್ವಾ? ಬೇರೆ ಝೂಮ್ ಅಕೌಂಟ್ ಇಂದ ಮಾಡ್ಬೋದಲ್ವಾ? ರ್ಯಾಂಡಮ್ ಝೂಮ್. ಸ್ಕ್ರೀನ್ ಎಕ್ಸ್ಟೆಂಡ್ ಮಾಡುದಾ? ಹೌದಾ, ಡೈರೆಕ್ಟ್ ಅದಕ್ಕೆ ಅದರ ದೂರ ನಿಮ್ ಕೇಬಲ್ ಸ್ಮಾರ್ಟ್ ಬಿಲ್ ಒಂದು 4 ಕಾರ್ಯಕ್ರಮ ಸ್ಮಾರ್ಟ್ ಬಿಲ್. ಹೌದು.
Oh, this is fine. For talking to someone who is here, like, not show them, right? Yes, not under. For people to see if you're not. First talk is of Abraham Berman, right? First was listening then. Possible to add equal so that whether calculator will be right in case gets disconnected we can again right that we have to invite you again the subject is quality. You got program now? Yeah, we have it. At what time? No, at this. When does the investor talk start? Oh, like you asking for what? Because we usually have a class at this time, right? 10:30. Whole day program. Whole day program. Okay, okay, fine, it's okay. But it's a whole day program. Yeah, I guess it starts at 12:50. 12:50? 10:50, 10:50. Oh, yeah. Thank you. Yeah. Oh, yeah. आपण प्रचार म्हटलं Vinay sir, can you tell me the passcode of the meeting?
Password of the meeting.
Passcode, yeah.
Eight six three four two nine.
Okay, fine. Vinay sir, I will do that to you in the evening actually, because now if I make some changes, then it may affect, we change the meeting link or something like that. If I edit the.
Link, then don't. So it's not possible to add to an existing.
Yeah.
Then don't. Okay, then what I'll do is I'll save it. I'll just save it in the text file.
Okay.
The begin copy paste.
There is a meeting, just you can, program. So, what? In the meeting, you can, feel that.
Oh. Audio also I won't, this mic I won't unmute, right?
No.
That will
Yeah.
go to Zoom, correct?
Iclaa. One thing is, the mic, right? Dad has to talk to the mic itself.
Yes. ಇದಕ್ಕೆ ಡೈರೆಕ್ಟ್ ಲಿಂಕ್ ಮೈಕ್
ಹೌದು ಸರ್, ಇದು ನಮ್ದು ಸ್ಪೀಕರ್ಗೆ ಎಲ್ಲಿದ್ದು
ಅಲ್ಲಲ್ಲ ಮೈಕ್ ಇಂದ ಇಲ್ಲಿ ಇನ್ಪುಟ್
ಹೌದು ಸರ್,
ಮೈಕ್ ಇಂದ
ಬರ್ತದೆ.
Can you check whether it is audible there if I am speaking? It should be because there is it's displaying some.
ನನಗೆ ಅವ್ರ ಮುಖ ನೋಡ್ತಿದ್ರೆ ನನಗೆ ಫೀಲಿಂಗ್ ಬರೋದಿಲ್ಲ ಮತ್ತೆ ಅವರು ಇದು ಮಾಡೋಕ್ಕಲ್ಲ ಅವರು ಇದು ಮಾಡ್ತಾರೆ ವಿಡಿಯೋ ಆನ್ ಮಾಡಿ ಬಿಟ್ಟಿಲ್ಲ ಆನ್ ಮಾಡಿ Hello. Hello, Avi, can you hear me?
Yes, I can hear you. Can you hear me?
I can hear you clear.
Okay, great. Thank you.
Thanks for joining us once again. Professor Kirkland will be coming very soon. Is he here around? He's taking coffee and coming back very soon, and he will be chairing the session.
Excellent.
Yeah, thanks a lot for being the resource person for the workshop. So I could talk to you after the workshop, your lecture. Anyway, thanks a lot. Hello?
Okay, I didn't understand.
Did we miss whether the audio was continuous and clear?
Sorry.
Our problem. No, this should not happen. What is the, how can we manage that?
Can you see the slides?
Yeah, we see your slide very clearly.
Okay, so I'll start when you tell me, when after
Okay.
introduction by.
Okay, please wait for a few minutes. Iclaa and other audience will be coming. Now we had after inaugural session, we had a photo session which took a little more time than expected, and they are taking tea and coming up now. Okay, thanks for waiting.
Morning ಅಲ್ಲ ಗೊತ್ತಿಲ್ಲ ಇದಾರ ಇಲ್ಲ ಇದಾರೆ ಆದ್ರೆ ಇದು ಡಿಸ್ಕನೆಕ್ಟ್ ಆಗೈತೆ ಯೂಸ್ ಆಗಿಲ್ಲ ಒಟ್ಟಿಗೆ ಏನಾಗಲ್ಲ ಚೆಕ್ ಮಾಡಿ ಹಾ ಅವ್ರು ಇದಾರೆ
Hello, sir. Burman, sir. Are you online?
Yes,
Yes, we'll begin in 1 minute.
excellent.
Yes. Excellent, sir. Thank you. Welcome back to the session. So this session will be chaired by Stephen James Kirkland, sir. Sir, over to you.
Good morning, everybody. My name is Steve Kirkland. I'm from the University of Manitoba in Canada. It's my pleasure to chair this first session of the conference for two reasons. One, it's the first session. Two, the speaker's a friend of mine. It's Avi Berman from the Technion Institute in Israel. Avi is well known for his work on non-negative matrices and matrices, CP rank, combinatorial matrix theory, and spectral graph theory. And it's this last topic that he'll address where he'll be telling about some families of graphs that are determined by their spectrum. Take it away, Avi.
Okay, can I start?
Please do.
Okay. The Turan graphs is an important class of matrices of graphs denoted by T and K, and the same notation, slightly different, denotes another important class of graphs, the graphs of pyramids. And what I'll show in the talk is that both classes TNK and TNK, this is a difference in notation, are determined by the spectrum. The outline of the talk is, we'll start with some background, talk about the graphs of pyramids, then about complete bipartite graphs, and then the two-rank graphs. A graph is a set of vertices, and two vertices are adjacent, they form an edge. So an edge is a graph is finite if it has a finite number of vertices, and it is simple if there are no parallel edges or loops. In other words, the number of edges between two vertices is at most one. In this talk, all the graphs are finite, simple, and undirected. If you look at the graph on the right side, this is an example of a directed graph with a loop. If we want to make this graph simple and undirected, we delete the loop and change the orientation of the edge from one side direction to both. And this gives us a graph of two vertices, two adjacent vertices, which is K2, a complete graph on two vertices. It's also P2, a path on two vertices. It's also C2, a cycle on two vertices. And another example on the left is a complete graph on 5 vertices, K5. Spectral graph theory studies the relations between the structure of a graph and the eigenvalues of matrices associated with a graph. And the matrices can be the adjacency matrix, or the Laplacian, or the signless Laplacian, or the normalized Laplacian. Another example is the distance matrix. In this talk, we consider only the adjacency matrix. A recent survey, it's a survey and also some new research results on spectral graph theory, is a paper by Igal Sasson, Noam Krupnik, Suleiman Hamoud, and myself, published recently. Igal is a professor of electrical engineering and mathematics at the Technion. Noam is completing his master in the computer science at the Technion, and Dr. Hamoud is teaching in the Department of Mathematics. If G is a graph with n vertices, V1, V2, Vn, the adjacency matrix of G is a 0, 1, n by n matrix, where Aij is 1 if and only if Vi and Vj are adjacent. So if they are adjacent, Vi and Vj is 1, and if they are not, then it is 0. When G is undirected, then Ag is symmetric and has real eigenvalues. And when G is also simple, the diagonal entries are 0. And most of the matrices in our talk will be symmetric, and so the eigenvalues are real. We denote by Sn the set of n by n real symmetric matrices. The spectrum of a graph is the multiset of its eigenvalues. Multiset because we include multiplicities. The multiset of the eigenvalues of its adjacency matrix. Two graphs are cospectral if they have the same spectrum. For example, if we look at the star S5, its adjacency matrix, as most of the entries of the adjacency matrix are 0, except ones on the first row and the ones in the first column. The spectrum of the star of S5 is -2, 0 with multiplicity 3, and 2. It is not a coincidence that the spectrum is symmetric with respect to the origin, because this is a property of bipartite graphs. Here is an example, a classical example of how what we can learn from the eigenvalues of the matrix. Suppose the lambdas are the eigenvalues of a graph G, then the number of edges of G is 1/2 sum of lambda I squared, 1/2 of sum of the squares of the eigenvalues. And the number of triangles is 1/6, 1/6 of the cubes of the eigenvalues. And the reason for it is that if we look at the case power of the adjacency matrix, its ij entry is the number of walks of length k from I to j in the graph. So the number of closed walks of length 2 from I to I in G is the I entry of A squared. And the number of closed walks of length 3 from I to I is the I entry of A cube. So the number of edges is 1/2 of the trace of A squared, which is 1/2 of the sum of lambda I squared, and we divide by 2 because each edge is counted twice. Similarly, the number of, I'm sorry, this shouldn't be edges, the number of triangles of G, triangles, not edges of G, is 1/6 trace of A cube, which is 1/6 sum of lambda I cube. Again, each triangle is counted 3 factorial times, so we divide by 6. We say that a graph is determined by its spectrum, denoted by ds, if every graph that is cospectral with G, has the same eigenvalues, is isomorphic to G. So the only way for two graphs to have the same spectrum is that they are isomorphic. Kn, the complete graph on n vertices, Cn, cycle of n vertices, Pn, a path on 5 vertices of n vertices, the complement of Kn, that is isolated vertices, and bipartite graphs with the same number of vertices in both parts are all examples of graphs that are determined by the spectrum. Also, all the small graphs, all the graphs with less than 5 vertices are determined by the spectrum, and all the regular graphs with less than 10 vertices are determined by the spectrum. In fact, when the study of spectral graph theory, or the question of spectrum of is the graph determined by the spectrum came out in chemistry, and at that in beginning it was thought that every graph, that all graphs are determined by the spectrum, but this is not true, and there are non-isomorphic cospectral graphs. For example, if we look at the same stars that we had before, S5, and we also look at a square with an additional vertex, C4 union K1, these two graphs have the same spectrum as before, -2, 0, 3 times, and 2, but they're clearly non-isomorphic because the star is connected and the other graph is not connected. Hammers conjectured that almost all graphs are determined by the spectrum. So the original question by the chemist was, so conjecture was that all the graphs are. Hammers' conjecture is that almost all graphs are determined by the spectrum. It is interesting conjecture, still open. In some way, it contrasts a result of Schwenk that said that almost all trees are not determined by the spectrum. But it's not a contradiction because trees are only a very special class of graphs, but here we have the Hammers conjecture. So this is the background, and now the definition of graphs of pyramids, and first some motivation. Some of you attended the workshop and I spoke about completely positive matrices. So let me recall that a matrix is completely positive if it can be decomposed as the product of B times B transpose, where B is element-wise non-negative matrix. Obviously, a completely positive matrix is positive semi-definite, it's B times B transpose, and it's element-wise non-negative because it's a product of two non-negative matrices. So it is doubly non-negative, non-negative in both senses. The elements are non-negative and the eigenvalues are non-negative in a symmetric matrix. And we say in this case that AA is a matrix realization of a graph G with vertices V1 up to Vn, if and only if Aij is non-zero, when Vi, if and only if Vi and Vj are adjacent. Not every doubly non-negative matrix is completely positive. It is true for small graphs, but not for graphs from order or for matrices lengths of order 5 or more. So we say that a graph is completely positive if every doubly non-negative matrix realization of the graph is completely positive. An example is the graph Tn that consists of n minus 2 triangles with a common base. And in two years ago, I think, I gave a course on matrix theory, and one of the problems was to check that Tn is completely positive on the way to prove the theorem written behind that I'll mention in a minute. Noam at that time was an undergraduate student, and he took this. The course was a graduate course, but he took this course, and of course solved the problem. But another related problem was to prove that Tn is also determined by the spectrum. That was another topic that we covered in the course. And then Noam suggested that perhaps we can extend this result to a more general set of graphs, and this is a TNK that I'll mention in a minute. Coming back to the question, to the characterization of completely positive matrices, Natalie Kogan proved in her thesis that in 1988, that the graph is completely positive if and only if it does not contain an odd cycle of length greater than 3. And by a theorem of Trotter, this is the same as saying that the line graph of the graph is perfect. So here is the definition of the set TNK. TNK is a graph that we get by it's a set of graphs, okay, TNK is obtained by taking a complete graph KK, and add to it n minus k isolated vertices. So in the case that the clique was K2, we gave the graphs Tn. But in general, we can consider the graph as pyramids with a common base, where the base is a clique. So T63 is an example of pyramids having a triangle as a common base. T62 is a set of triangles having a common base. And T61 is a star. So again, for k equals 1, Tn1 is a star. For k equals 2, it's Tn. And in general, for k greater than 1, we call the graphs Tnk graphs of pyramids. And the question was to prove, the idea was to prove that these graphs are determinable by the spectrum. And the first thing to do was, of course, to compute the spectrum of the graph. So the spectrum of the graph consists of 4 different eigenvalues. Lambda 2 is a spectral radius, lambda 1 is a negative eigenvalue. Lambda 1 and lambda 2 are roots of a quadratic equation given here, and minus 1 has multiplicity k minus 1, and 0 has multiplicity n minus k minus 1. The way to compute, one way to compute the best way to compute the spectrum is to use the concept of Schur complement. If M is a square block matrix, A, B, C, D, where D is non-singular, its Schur complement M over D, the Schur complement M over D of D in M is A minus B, D inverse C. The name Schur complement was coined by Emily Ainsworth, and Schur proved that the determinant of M is the determinant of D times the determinant of the complement. And similar result is for the rank. The rank of M is the rank of D plus the rank of the complement. Schur, of course, has many theorems in algebra in general and in linear algebra in particular. Many years ago, I gave a course on the basic course on linear algebra, and we talked about Schur's triangulation theorem. And in the final, I gave a bonus problem, a bonus question, which asked, where is Isai Schur buried? Where is the grave of Isai Schur? And in what experiment, what instrument did the son of Otto Teplitz play? Isai Schur and Otto Teplitz were two of many Jewish mathematicians in Germany who had to live, luckily they could live because of during the Nazi invasion, and they both came to Israel, Palestine at that time, and Isai Schur is buried in the Trumpeldor Cemetery in Tel Aviv, which is an interesting historical cemetery. And the son of Otto Teplitz was a professor in Bonn, and Isai Schur was a professor in Berlin. And the son of Otto Teplitz was the chief flutist of the Israeli Philharmonic Orchestra. What happened is students usually prepare, when they prepare to the final exam, study earlier exams. So what happened is that about 10 years after I gave this problem, this was many years ago when I taught this course, students would come to my office and ask, where is Isai Schur buried? So that's the story, my personal story of Isai Schur. And the theorem that we proved with Noam is that the graphs of pyramids are determined by the spectrum. And we can see that the theorem supports the Haller's conjecture. Here is the outline of the proof. First, suppose G is a graph cospectral with T and K, for K greater than or equal to 2. As a spectrum, first, if they are cospectral, they have the same spectrums that we had before, lambda 1, minus 1, k minus 1 times, 0 and minus k minus 1 times, and lambda 2. And we want to show that G and T and K are isomorphic. A key tool in the proof is Cauchy interlacing theorem. If B is a principal submatrix of an n by n symmetric matrix, if B is n minus 1 times n minus 1 principal submatrix of a symmetric n by n matrix A, and if the lambdas are the eigenvalues of A and the mu's are the eigenvalues of B, then the mu's interlace the lambdas. Lambda n is less than equal to mu n minus 1, is less than equal so on to mu 1,
less than equal to lambda 1. And this is a very useful theorem in spectral graph theory. And here is the outline of the proof. First, we show, we use again, we use in these several lemmas, we use Cauchy's interlacing theorem. First, we show that G does not contain a clique of size k plus 2. It does not contain the subgraph of k with k minus a complete subgraph with k minus 2 vertices, because G has k negative eigenvalues, we saw, but the clique of k plus 2 has k plus 1 negative eigenvalues, so the lemma follows from the interlacing theorem. Then we show that G does not contain a path of length 4 as an induced subgraph, and the proof is similar because G has one positive eigenvalue, while the path has two positive eigenvalues. And the third lemma is that every two non-empty induced subgraphs of G are connected by an edge. Suppose not, then there are two disjoint non-empty induced subgraphs, H1 with V1, E1, and H2, V2, E2, such that the H, the subgraph induced by V1 and V2, has at least two positive eigenvalues, since this is its adjacency matrix, and this contradicts again the interlacing theorem. And then we show that suppose H is a maximal clique in G. So again, G is a graph that is co-spectral with T and K, and we want to show that they are isomorphic. But then we observe that, or show that if U and V are vertices of G but not in H, then they are not adjacent. For example, we can see it on T6. Every triangle is a clique, it's a maximal clique, and all the other vertices are not adjacent. And the proof of the lemma involves checking several cases that we want to use, and uses the condition that k is greater than 1. And then, returning to the theorem, we suppose that the size of the largest clique is m. By the first lemma, m is smaller than k plus 2. So its adjacency matrix can be written as in a block form as J1, Jk plus minus Ak plus. That is, J is a matrix of all ones, and I is the identity. B in this case is a block matrix, and using the effect that G and T and K are cospectral, they must have the same number of edges, and this implies that M is equal to K plus 1, and all the entries of B are also equal to 1. And this shows what we wanted to show, that G and T and K are isomorphic. And now we go to the third part of the talk and talk about complete bipartite graphs. Recall that the graph is bipartite if its vertex set is a disjoint union of two subsets, left and right. V is L union R, such that no two vertices in the same subset are adjacent. We say that G is a complete bipartite graph if it is bipartite, and every vertex in L is adjacent to every vertex in R. The graph on the right is complete. We have two vertices on one side and three vertices on the other side, and all three vertices are connected to the two vertices. The graph on the left side is bipartite, but it's not complete. The following properties of a graph are equivalent. G is bipartite. This is the same as saying that G does not contain an odd cycle. And this is the same as saying that the spectrum
of G is symmetric with respect to the origin. And we want to compute the spectrum of KPQ of KPQ is a bipartite graph with P vertices on one side and a complete bipartite graph with P vertices and Q vertices. And the claim is that the spectrum consists of square of P times Q as a spectral radius minus the square of P times Q is a negative eigenvalue, and 0 appears n minus 2 times. And a simple way, a very elegant way to prove it is to look at the adjacency matrix. It has 0 blocks on the diagonal and blocks of ones off diagonal. Its rank is 2, so the trace is 0, and this implies that the spectrum is L minus L and 0 n minus 2 times, and where L is a spectral radius, but the number of edges is L squared. L squared is P times Q, so L is a square root of P times Q as we claim. Recall the arithmetic mean, geometric mean theorem. Let P and Q be 2 natural numbers. The arithmetic mean is, as you remember, is 1/2 of the sum, and the geometric mean is a square root of the product. And we say that a pair PQ of natural numbers is an AM minimizer if it attains the minimum arithmetic mean for a fixed geometric mean. Examples are when P and Q are the same, or when P and Q are prime numbers, or when P is equal to 1 and Q is prime. And Andre proved the theorem that we can reformulate in terms of AMGM in the following way. The complete bipartite graph KPQ is determined by the spectrum if and only if the pair PQ is an AM minimizer. And here are several examples. The examples of the right are determined by the spectrum because the PQ is an AM minimizer. The example on the left is not determined by the spectrum because this graph is cospectral with, if we take K44 and add n isolated vertices. I want to describe a new proof, a different proof than the proof of Andre by Yigal Sasson, Noam Krupnik, and Suleiman Hamoud, and myself. And here is how the proof goes. If P and Q is not an AM minimizer, then they are a natural numbers A and B, such that they have the same geometric mean, but the arithmetic mean of AB is smaller than the arithmetic mean of PQ. So we take R to be A plus B minus P plus Q, it's positive, and we consider the graph KAB union with R isolated vertices, and the graphs G and KPQ are non-isomorphic cospectral graphs. On the other direction, if P and Q is AM minimizer, then G is graph, and G is a graph cospectral with KPQ. We want to show that they are isomorphic. If A has the same number of edges in KPQ, first A has the same number of edges as KPQ, so the number of edges in G is P times Q. It is bipartite, and we show that G is complete bipartite. We show that now this is outline of the proof. We show that G is complete bipartite, hence J is isomorphic to KPQ. And as a corollary, we get that the star graphs, this was the case where in T and K were case 1, the star graphs are determined by the spectrum if and only if they have a prime number of edges. The most complete bipartite graphs are not determined by the spectrum, and this does not support the Hammer's conjecture. But regular complete bipartite graphs are determined by the spectrum. Now we go to the last part of the talk and talking about two-one graphs. A graph is k-partite. Bipartite was the case where k equals 2. A graph is k-partite if its vertex sets can be partitioned into k subsets and there is no edge between two vertices. And the k-partite graph is complete if every two vertices in different subsets are adjacent. And the graph is multipartite if it is k-partite for some k, and the graph is complete multipartite if it is complete multipartite k-partite for some k. The complete multipartite graph with subsets of sizes n1 up to nk is denoted by k, n1, n2, nk. And this is an example of k, n minus k, and many ones, several ones. And this allows us to define the two-one graph Tnk. Tnk is a complete k-partite graph on n vertices, where the sizes of the subsets are equal as positive. If n is qk plus s, then Tnk is k q plus 1 up to q plus 1 s times, and q to q and k minus s times. And so these are examples, and we can compute the number of edges in T and K, and the number of edges is n choose 2 minus s times k plus 1 choose 2 minus k minus s q times q choose 2. And two-one theorem is a fundamental result in extremal graph theory, and it shows that a graph G on n vertices with maximal clique of size q of size k has at most e n k edges. A special case is Mantel's theorem about triangle-free graphs. A triangle-free graph on n vertices has at most n squared over 4 edges. This is of course called two-one, and there are many proofs of the theorem. It's a very important theorem. Very beautiful proofs are described in chapter 41 of the book. It's a lovely book, proofs from the book by Martin Eigner and Gunther Ziegler. The idea, the name of the book comes from what Paul Erdős used to call the book. Paul Erdős said that there is a book, a divine book, that contains, written by God, that contains all the beautiful proofs of theorems, and for a mathematician to prove a result, to find a nice proof of the result, is to find the result that appears in the book. So Eigner and Ziegler collected very beautiful proofs. Some of them, as I said, is in chapter 41 in the book. A personal note on Paul Erdős. The first time that I met him was when I was in high school, and Professor Hanani brought him, was my teacher in high school, also in the technical later, and brought him to our class. And then I had the privilege of taking several courses and many discussions with Paul, because he was what we call a permanent visiting professor at the Technion. Permanent visiting professor means that whenever you come, you immediately get your office and some salary. Again, a theorem by Ma and Re that I mentioned before shows that the Turan graphs are determined by the spectrum, and we observe that this does support the Amos conjecture. And I want to outline a different proof, again, in the paper by Yigal Sasson, Noam Krupnik, Suleiman Hamoud, and myself. And here is the idea of the proof, of the outline of the proof. Let G and T and K be co-spectral. And we want to show that they are isomorphic. We use the theorem of Smith that says that if a graph G has exactly one eigenvalue, then no isolated vertices of G form a complete multipartite graph. Then we show several things. We first observe that the inertia of T and K is 1 n minus k, k minus 1. There is one negative eigenvalue, k minus 1 positive eigenvalues n minus k, and multiplicity of n minus k is 0. If G has no isolated vertices, we show that G has no isolated vertices, so it is a complete bipartite. We show that A has no clique of size k plus 1. We show that G is complete k-partite. And then we show that Ni is less than equal, all the sizes are less than equal to k plus 1 and greater than equal to q. So they are between q and q plus 1. And at this point, we show that like T and K, G is k-partite and the sizes are q or q plus 1. Suppose we have alpha subsets of size q and beta sizes of size q plus 1. Then we have a system of a simple linear system, q plus 1, 1, 1, alpha, beta equals nq, nk, and this system has a unique solution. The determinant is non-zero, and so it's isomorphic. So G is isomorphic to T and K. So let us summarize what we try to show. For natural numbers k less than equal to n, the Turan graphs T and K are determined by the spectrum. If k is equal to 1, the star T and 1 is determined by the spectrum if and only if n minus 1 is prime. If k is greater than 1 and less than equal to n, the graph of pyramids is determined by the spectrum. And this concludes the talk, and I thank you very much. And you can observe that all components of the thank you except K are determined by the spectrum. Thank you very, very much.
Thanks very much, Avi. We have time for a quick comment or question.
I have to apologize. I have difficulties understanding possible questions. So if you have questions, please mail them to me and I will be very happy to answer what I can. Many thanks. I want to say that I am very happy to be here in ICLAA, but unfortunately, I can do it only through Zoom. But thanks.
I have no question, Avi, but I'm happy to see you and listen to your talk. I wish you were here. Thank you for that.
I wish I would be. Thank you.
All right, so let's thank Avi Berman one more time for his lovely talk. And the next session will begin in a matter of seconds.
Yeah, thank you, sir. So now we move on to the next session of invited talks. So session will be chaired by Leena Malhotra, ma'am. Over to you, ma'am.
So just repeat.
This one was for the display. So this will be for left hand side. Left hand side. Please open it. So there is December 2025. So in that, what are the files?
Paper 1 AAA and
No, no.
for 1988.
No, no, no. We use the other one.
Oh, okay, okay. Manipal top 25?
No, no.
Manipal 25.
Notice. Just a
other
minute.
stuff.
Give me the specs. This is for next stop, sir. Next stop.
Oh, okay. Yeah. Yes, sir.
Just it will not be shown there. No?
No, no, sure.
Just a minute. It is not. Don't show.
Okay.
No. Just a minute. Just
zoom in.
No. Just
This one? Should I display? MDU.
No. No.
So tell me the file name approximately.
No, just see the other one. This one.
Okay, sir. Okay, mic. Okay, yes.
So, welcome to this second session, and I am pleased to introduce Professor Samir Neogi from Indian Statistical Institute Delhi Center. And the talk, as you see, it will be devoted to 3 decades of propositivity and its applications in optimization theory. Please, Professor Neogi.
So I'll just check it. It's not okay. It's not it. Prasad approach to me. Yeah.
So I should give a talk which is different from what I gave. To summarize the kind of work we're doing it for so many years, and I have chosen a topic, a work on 3 decades of propositivity and its application in the optimization theory. Propositive matrices are it's well known to the researchers in those who are working on matrix analysis. And I'll tell, even though that you'll be surprised to know that it is the platinum jubilee year of propositive matrices. JOTA has a special volume devoted to 75 years of propositivity. And I'm working nearly, I'll say that little more than 2 decades on propositivity, and the title is this is okay?
Yeah.
This is fine. Okay. So 3 decades of propositivity.
So that mic has to go.
But okay. So here I will briefly introduce with a little history on propositivity and then I'll proceed with the research in the last 3 decades of co-positivity, and then mention about few problems on co-positivity. Perhaps that researchers will be interested to work on it, and still there is lots of problem to work with. The outline of talk as follows: that history of co-positive matrices, and matrices with non-negative principal minors. Everybody know that that those who are associated with matrix analysis, they know about PD and positive definite matrices and positive semi-definite matrices, P-naught matrices, and their generalization co-positive matrices over few decades, over 50-60 years. And lots of research has gone to it, and still people are working on positive definite and positive semi-definite matrices. And the type of matrices I will be talking about, many of them evolved from optimization problem, from linear complementarity problem, which unifies many optimization problem. And there are more than 50 matrix classes evolved in these 75 years. And out of that, maybe that we have developed around more than 10 or 15 matrix classes. It is due to us. So we'll be talking about the classes which are developed by us and other classes. So this is the kind of forum, no, that where we can talk about the matrix classes which are developed by us and the possible problems, and then theory of co-positive matrices and some of the co-positive tests which are available for these matrices. Those who are working on optimization, you will see that for the last 1 or 2 decades, there is lots of people are working on co-positive optimization problem, and those who are working, in fact, that we also wrote 1 or 2 papers on co-positive optimization problem associated with matrices that associated with the tree and the resistance distance matrices. So where we optimize something subject to something, and we saw that you find applications in game theory and other branches of algebra. If you look back, that the notion of co-positive matrices, it can be traced back to mostly 1952 and earlier work of Dience in the study of quadratic forms. So when we say that matrix is co-positive, if X transpose X is non-negative for all X belonging to Rn plus, so for all X non-negative. And initially, if you see the work, that they are working with understanding the co-positive matrices of low order, especially 2 by 2 or 3 by 3 cases. And then there are various researchers who are looking into it, including Kaplan, Portal, and Danzig. They are looking at the co-positive matrices in connection of the complementarity problem. Basically, that in the complementarity problem, the data matrix is M and vector Q. The M they assume to be co-positive. Now, there are various characteristics of co-positive matrices are available. If you look back the history, that one interesting characteristic was, if you have a co-positive matrix, whether we can express it as a positive semi-definite matrix and a non-negative matrix, plus a non-negative matrix. And so, and then the other motivations are that, as I mentioned, that since it is a generalization of PhD matrices, that researchers are interested that what kind of results that which are available for positive semi-definite matrices, you can extend it for co-positive matrices. So therefore, in general, the set of all PhD matrices, if you look at, it's a small subset of the set of all co-positive matrices, and PhD properties are not all applicable for co-positive matrices. And we are trying to understand the difference between co-positive matrices and positive semi-definite matrices. And I'll make use of these terminologies: C0 for co-positive, C for strictly co-positive, PD for positive definite, PSD for positive semi-definite, and SN for symmetric non-negative. All of you are aware that about positive semi-definite matrices. So there we demand X quadratic form that X transpose X is greater than or equal to 0 for all X belonging to Rn. And it is positive definite, it is strictly greater than 0 for non-zero X belonging to Rn. And in 1969, Bella Matos that generalized this positive semi-definite matrices for symmetric case, and it is defined as positive subdefinite matrices which contains positive semi-definite matrices. Maybe all of you are aware that when we talk about a positive semi-definite matrices, we always write symmetric. Reason being that it is if you write A plus A transpose, no, that it gives A is positive semi-definite if and only A plus A transpose is positive semi-definite. Now this positive subdefinite matrices, it contains positive semi-definite matrices, and the way to define a positive subdefinite matrix is X transpose X less than 0 imply A transpose X is inside. Okay, and examples are, you can see that if A is a PSD, then A plus A transpose is also a PSD, but here it is not. First example is the example of a positive subdefinite matrices. You can see that X transpose X less than 0 will imply A transpose X is uniside. Either it is less than or equal to 0 or greater than or equal to 0. Now we can see that the other one, that A is PSPD implies whether A plus A transpose is a PSPD. It will not go through for PSPD matrices. This is the counter example. Similarly, it is well known that if A is a PSD matrix, A inverse is a PSD matrix. But this will not hold. That A inverse is not a PSPD matrix. Okay. So it will be interesting to find out under what condition that A inverse will be a PSPD matrix. Okay, so this will be interesting, and perhaps I'll give some more open problems related to PSPD matrix. But we observe that if it is PSPD intersection copositive matrix, then it will be a P0 matrix. That is matrices of principal minus non-negative. And all of you are aware of what is principal submatrix, and this is the determinant of that if the determinants all principal minus and non-negative, then it is a P0 matrix, and it is easy to see that this class has a completeness property. These are the definitions. Some of the definition I will need. That the G matrix is all off diagonal entities and non-positive. Study of global equivalence in economic theory, linear complementarity problem, game theory, and engineering applications. You will see that application of copositive matrices and its subclass are abundant. You will find that there are many there in the literature. So this is the definition of complementarity problem, that in India there are few groups that who are working in such problems. One is from IIT Madras, Professor Siva Kumar, and maybe from ISI, and there are some other groups from Srinagar and all. So they are working on linear complementarity problem. And so where typically we demand that you have to find out vectors W and Z such that 1 and 2. It is called a Q matrix if this is linear complementarity problem, and if it has a solution for all Q belonging to Rn, then you will say that it is a Q matrix. Otherwise, that we can still define that when it has a feasible solution, LCVQL we have solution, then the solution set will be non-empty. feasible set is non-empty implies the solution set is non-empty, then such matrices are called Q-naught matrix. So you can see that investigation of all kinds of that around 30 or 40 classes of matrices, it relies on that assuming that whether M, the properties of the matrix A. And most of the matrix classes evolved based on the properties of them. And you may wonder that from where copositive matrix came in the context of linear complementarity problem. Lemke in 1965, so he came up with a subclass of linear complementarity problem. So there he assumes M is a copositive class matrix. And all games know that, all bimatrix games know that he could write it in such a form that matrix M is a copositive class, that it is a subclass of copositive matrices for which the algorithm works. And that triggered the researchers on matrix theory to work on this. And you may wonder that it started in 1965, whether such kind of research is relevant or not. You will see that Europe or UK, there are plenty of people, those still working on finding the Nash equilibrium, number of Nash equilibrium. In fact, that there are some open problems. If you have n, no, that more than 4 or 5, no, that number of Nash equilibria, that upper bound, no, that it is still that such kind of conjectures are open, and there that copositive subclasses of copositive matrices plays a big role. Now, while defining subclasses of copositive matrices, here I'll use principal pivot transform in terms of many of the classes of copositive matrices are defined in terms of principal pivot transform. And many of you know that it is introduced by Tucker, and it has applications in mathematical programming, complementarity problems, statistics, matrix analysis, and many other areas. So, it is relevant, and principal pivot transform is defined like this. Principal pivot transform with respect to alpha, for which determinant M alpha alpha is non-negative. So here that when we talk about a principal pivot transform with respect to alpha, we'll have that this kind of principal pivot transform are called legitimate PPT, for which that we take a PPT where that M alpha alpha is non-singular. Okay. And so these are the characterizations. Many of these characterizations, you know that P and P matrices, that eigenvalues are positive. A reverses the sign of non-zero vector, and unique solution. If M is a P matrix, it is known that this class P has a that LCM Q has a unique solution for every Q belonging to Rn. In fact, that if you draw if you draw the complementary cones, so no complementary cones will be overlapping for P matrix. And so similarly, there is a generalization of results in case of P-naught matrix, where all principal minors are non-negative. So these are the results which are available in Cottle-Plankstone's book. Now, let us talk about various subclasses are introduced. I said that when in 75 years of study on copositivity, there are various people who are no way connected with linear complementarity problem. So they are looking at copositive matrices on a different angle. But there are researchers who are from optimization or game theory. They are looking at the analysis of copositive matrices on a different angle. Okay, and strictly copositive or copositive plus. So this matrix evolved in that connections. So in strictly copositive, we want that X transpose X is strictly positive for non-zero X, for non-zero non-negative X. And copositive plus means A has to be a copositive matrix, and plus this additional condition has to hold X transpose Ax equal to 0 x greater than equal to 0 implies A plus A transpose X equal to 0. In 75, 76, no, that lots of people are working on co-positive plus and strictly co-positive matrices, and their work on Jones by Jones, no, where that they are investigating that whether you take any matrix, if you can write it as a co-positive matrix, co-positive plus matrix and a non-negative matrix, then and certain inequalities are satisfied, then Lemke's algorithm will go through. So such kind of results, no, people started with various combinations and tried to see that apart from the co-positive plus class which was proposed by Lemke, what are the other subclasses for which Lemke's algorithm will go through. So this is one line of research. Apart from that, there is another group of people like Ives, Garcia, Doversby, Todd. So they are working, they are trying to generalize Karmadian. So they are trying to generalize the classes of co-positive matrices. And in those connections, that various generalization came, like semi-monotone, which is defined like this. So if you have a non-zero non-negative y, there exists an I such that yi greater than 0 and ay greater than equal to 0. So such classes are semi-monotone. And you will see that for all such matrices, whether it is a co-positive matrix or semi-monotone matrices, their principal submatrices are also co-positive and semi-monotone. And these are some of the old results. No, if you have a co-positive matrix, diagonal elements will be non-zero, and these are the observations you will see in the literature in the old literature. And I'll mention about one more result. No, that a matrix is called exceptional. Normally in the co-positive, no, that this was termed as exceptional. In general, it will not be true. A matrix is called exceptional if it is not the sum of PSD and then non-negative matrix. So if you see that up to order 4, you can express any co-positive matrix as a PSD matrix and a non-negative matrix. But this will break down if n is greater than or equal to 5. So it is interesting to know at this point that what is the condition you can impose so that this will go through. For even greater than or equal to 5, it will go through. And what went wrong that when you are considering dimension more than 5. Okay. Now, reason being that what is the motivation of investigating such problem? If it is a PSD plus a non-negative matrix, you will see that there are nice algorithms available, so it will be interesting to work. No, that algorithmically this will be a very useful class if somebody is investigating that for the class of CNOT matrices, under what condition you can write it as a non-negative matrix plus a PSD matrix. Okay, and okay, so this was the counter example. Okay, where that you have this is called Horn matrix, and this was proposed long back that it is a counter example of order 5, a co-positive matrix that which cannot be written as a PSD matrix and non-negative matrix. So I think okay. Now there is another group, Valiavo and others. They have started looking at almost co-positive matrices. So that means all n-1 order is co-positive, but nth order is not co-positive. And you know that those who are working on inverse co-positive matrices, this is one such that if you take the inverse, it will be a G matrix. It will be a G matrix. So that way it was interesting. But I believe that almost co-positive matrices are also not fully explored. So still there is a lot of scope to work with. I'll give some direction, and similarly you can have that almost strictly co-positive, almost co-positive plus, where you will demand up to n- order is co-positive and higher order is not. And this tends us to define a class of complementative problem, co-positive complementative problem. You know that co-positive optimization problem. So that a number of people in Europe, they are working on co-positive optimization problem, and there is a very strong group. So similarly, we can have this one, the detailed study on co-positive complementarity problem, where that will investigate under what condition, no, that where M is a co-positive matrix, and under what additional condition is needed, it will be processed by Lemke's algorithm, or it will have nice structure. And another thing is that if the matrix is very large, you will not be able to do any kind of pivoting algorithm, will not be good. So you may like to use the interior point algorithm. Kojima and others, they talked about various interior point algorithms, but they have also they have a limitation. It works only for subclass of copositive, subclass of P-naught matrices, and they are also copositivity somewhere entering into the picture, which Kojima didn't investigate, so that needs to be investigated. But you need to have some idea, no, that where that people, those who are good in computation, so you have to take such kind of matrices and see that how it works. Okay. Now, when we talk about copositive matrices, that as I said, that P-naught matrix came into picture, and among P-naught matrix, there is a very nice class which is called sufficient matrices. And sufficient matrices, the matrix is said to be column sufficient. If xi axi less than equal to 0 implies xi axi equal to 0. And if A transpose is column sufficient, it is row sufficient. And if A and A transpose is column sufficient, then we say it is a sufficient matrix. Now you may wonder that why we will be interested in sufficient matrices. So this is in connection that there are very nice algorithms that when M is a sufficient matrix. So this is the precise reason that we would like to investigate what is the subclass of copositive matrix which are sufficient. We know that entire copositive class is not possessible by Lemke's algorithm or not possessible by any interior point algorithm. But what is the subclass? You can say that they are very much possessible. In fact, you may get some of the cases that polynomial algorithm or even for a linear complementarity problem. In general, that algorithms for a linear complementarity problem is NP complete. So we are working that, so we went through a different direction. As I mentioned that there are two class of group of researchers like Iwsmga, Garcia, etc. So they are generalizing C-naught matrices. Then another group from ISI, they are looking at PPT based class, PPT principal pivot transform based class. So here there are classes like fully copositive. Fully copositive means if it is a copositive in all its PPT, that kind of matrices are called fully copositive. Yes, 5 minutes. Okay. And if it is only some of the PPTs either C-naught or almost C-naught, it is called almost fully copositive. So that a group of researchers looking at it, and it was found that if it is almost C-naught F intersection Q-naught, it is a P-naught matrix. And getting an example for almost C-naught matrix, almost fully copositive, it is not easy because you have to see that all its PPT and all, no, that is not that easy. So this is an example of almost fully copositive matrices. And these are some of the results I can skip. And then we have some of the subclasses of P-naught matrices based on the PPT. Now that you have seen that Johnson's paper where we talk about inverse G matrices. So here that we can generalize that problem that at least one PPT is a G matrix. There is a spelling, okay. Or at least one of the PPT is copositive plus or strictly copositive.
So characterizations of these classes of matrices are left open for a long time. And I believe that those who are planning to use work on this, so they can mention this conference that this is the open problem posed in this conference. Okay, and this is the optimization problem which can be used for copositivity testing. There are many algorithms, and M is a C naught if and only if f x bar is greater than equal to 0. So this is the kind of optimization problem. We have worked, myself and Bapat both worked on a problem on distance matrices associated with the tree, and where that we have this copositive expression, and we converted into a PhD matrix. So otherwise this problem is NP complete, and this we converted into a polynomial algorithm for solving it. So that's a very nice result, and later on we wondered whether that can be generalized for any other matrices. We generalized for resistance distance matrices, and this is the optimization problem which we solve. Then that will give this an answer whether the matrix is copositive or not. I believe that literature on copositive matrices are very rich. Many more, even though that in last 30 years we are not able to exhaust all the problems, still there are lots of open problems which people can work on it, even if you limit yourself to only two copositive matrices. Thank you.
Any questions? Any questions from the audience, comments, remarks?
The next slide, the thank you slide.
I think so. Let me see. It is 32. No, it is thank you slide only.
Thank you. You was expecting a good contestant to prove, right? But anyway, I think that we all thank Professor Neogi for this nice historical view of the copositivity theory. And I wish that somebody can prove.
That open problems?
Yes, exactly.
The people will work on it, and I'll be glad to answer that if you have a doubt at any step that or you get into problem of proving something, and so I'll be glad to help.
Yeah, we wish. So thank you, Professor Neogi.
As a token of appreciation, I request Leena ma'am to honor the speaker.
That's it.
Now the next speaker, Professor Tasmita Varitka from Bhubaneswar University. She will talk about integer matrices with integer eigenvalues and Laplacian integral graphs. Please.
So, good afternoon, everyone. And here I'll speak on integer matrices with integer eigenvalues. And also I'll tell about Laplacian integral graphs. Mainly one open conjecture that was given by Phalat and others. So this work is a joint work with my PhD student Subhasis Behra. So let us take a matrix, which I am taking a square matrix, n cross n matrix. And if all the entries are integers, we call it an integer matrix. And the characteristic polynomial then will be denoted by phi ax, and that will be a matrix with integer coefficients. So using rational root theorem, we can say that each rational eigenvalue will be integer eigenvalue, or a rational root is an integer root of the polynomial. So I'll consider the matrices basically which are having integer eigenvalues. So such things we'll study here. So this was the statement that Martin and Wong they posed, means they have observed that almost all integer matrices have no integer eigenvalues. That means given n greater than equal to 2, the probability of a random n cross n matrix has at least one integer eigenvalue is 0. So that means there are many matrices which are not having even a single integer eigenvalue. Then it's natural to consider the matrices which are having integer eigenvalues. So the questions comes like which matrices, integer matrices are with integer eigenvalues can we characterize, and is there any possible way to construct such matrices? We can also consider only non-singular case, non-singular integer matrices with integer eigenvalues. So these constructions are there in the past, and there are very nice construction. Here I'll give a simple construction that is known as Galvin's method. So if P is an integer matrix, I look for the determinant, and if it's not 0 and delta, then define the matrix delta P inverse, and that's obviously an integer matrix. Then if you choose integers lambda 1 to lambda n, where lambda is an integer multiples of delta, then we can take D as the diagonal matrix having lambda 1 to lambda n. In that case, if I construct the matrix A, that is P D P inverse, that will be a matrix with integer entries and it has integer eigenvalues. So this is a very simple construction, but it can give you such matrices. But this has many limitations also. Here we provide one necessary and sufficient condition when the integer matrix has all integer eigenvalues. This is the theorem, and this is of its inverse. So we have taken the non-singular matrices. This construction means this theorem works for non-singular matrices. So let A be a non-singular integer matrix. Then if we can write A inverse as a sum of rank 1 matrices in this way, choosing xi, yi, they are vectors in Q1. So with rational entries, and pi is a non-zero integer. We'll choose our vectors in such a way that yj transpose xi, that is 0, and yi transpose xi, that is 1 by pi. So if we can write A inverse in this form, then your A has integer eigenvalues. So this is a if and only condition. I don't know how much it will be useful, but the result is very nice, and I'll just give one example. That let us take x1 as 1 and minus 1 by 3, x2 2 minus 5 by 9. So I'm choosing rational numbers or integers in the coefficient, and y1 I have chosen half and 1, y2 1 by 3 1. So then you can see that the conditions of yi's and xi, those are satisfied, and then A inverse can be calculated as this. So I'm just taking vectors and then calculating A inverse. So in this case, you can observe A is coming at this, and it is the eigenvalue 6 and 9. So this is this way it works. Now we try to give two constructions for integer matrices and with integer eigenvalues. One is I used Hadamard product. So Hadamard product of two matrices is entry-wise product. So the entries of the product will be Aij, Bij, if Aij, Bij are entries of A and B. So if you take a diagonal matrix, diagonal eligible matrix A, and then suppose that A is written as MD M inverse, where your diagonal entries are the eigenvalues of the matrix. So those are lambda I. Then we can observe that AI that can be written in this form, that is sum of M Hadamard product M inverse transpose its IK entry into lambda K. So this way we can express. So this is the way if we construct. So this is, let us start with a symmetric matrix M, and which is a positive definite integer matrix. And then I'll choose A11 to ANN. They are the numbers chosen in such a way that AII, they are multiples of determinant of M Hadamard product adjoint of M. Okay, then if I choose the numbers lambda 1 to lambda n in such a way that this relation is satisfied, then the matrix MD M inverse, this matrix is a diagonalizable matrix with integer entries and integer eigenvalues. So this construction you can see through one example. Here I have taken the Laplacian matrix of K3 and then I added I. So this is a positive semi-definite matrix, a positive definite matrix. And then its determinant is 16. So accordingly, I have constructed this M Hadamard product adjoint of M. And that matrix is this. You can see the determinant is this. So I'll choose three numbers A11, A22, A33 as a multiple of this determinant. And then if I choose lambda 1, lambda 2, lambda n satisfying this, the earlier equation, this, then we can say that the matrix constructed taking D as diagonal matrix of lambda 1, lambda 2, lambda 3. That will be, if I take D, then A equal to MD M inverse. That is a matrix which is a diagonalizable integer matrix with integer eigenvalues. This approach, like I started with one positive semi-definite matrix, and I can construct family of, because here I have to choose only multiples of like A11, A22, A33. I can choose any multiple of that determinant. So given one positive definite matrix, we can go for a family of such matrices. Now another nice matrix is zero line sum matrix. So we constructed zero line sum matrices, which are integer matrices with integer eigenvalue. So we gave one construction. So zero line sum matrix is if each row sum and each column sum is 0. So those matrices are with less rank and they form a vector space. And 0 is always one eigenvalue, and the corresponding vector is the all ones vector. And also it has been proved that all the covectors of such matrix are equal. And one good example is the Laplacian matrix of any graph. That's a zero line sum matrix. So here if I am taking S, and S is formed in this way, x1 to xn minus 1. I'm choosing the vectors which are orthogonal to the all ones vector, and the last column is the all ones vector. Now consider a diagonal matrix. You can choose your lambda I, and lambda 1 to lambda n minus 1 you have to take, and 0 I am keeping because the matrix has 1, 0 identity. In such a way that lambda I is an integer multiples of n for exactly 1 I. And for I not equal to j, lambda j is congruent to lambda I modulo determinant of S. In that case, if I construct a matrix A, that is S D S inverse, this matrix is a zero line sum integer matrix and it has integer eigen. So this is another construction. So now I'll move to the Laplacian matrix and of a graph, and here we'll discuss about the graphs which are with integer eigenvalues. So Laplacian matrix is a 0, 1, 0 and minus 1 octagonal entry matrix. So the diagonal entries are the degrees, and the octagonal entries are minus 1 if the vertices I and j are adjacent, otherwise 0. So it's a matrix with diagonal entries of integers and off diagonal entries -1 and 0. It's a positive semi-definite matrix that we know, and it's again a 0 lines of matrix. So this matrix is well studied for graphs, and this question was posed by Harari and Swain, that which graphs have the integral spectra. So when I'm saying here integral spectra, basically I mean that Laplacian integral. Okay, the same question can be posed for adjacency integral also. So when he posed the question, he also indicated that this is a difficult question, and it will be difficult to characterize all such graphs. Because the number of integral graphs is not only infinite, but you can find them in all classes of graphs, even for all numbers for vertices. So for any n, you have one integral graph. So this was observed by Braun and Meris that Laplacian integral graphs are more frequent than the adjacency integral graph. So this makes it interesting to consider the Laplacian integral graphs. So what they proved is in the class of all trees, the stars are the only graphs which are Laplacian integral. So in the tree class, it's completely characterized, whereas in tree class, we don't know the answer for adjacency eigenvalues. So then, he proposed one method to construct Laplacian integral graphs from the known ones by adding one edge. So that was obviously a fundamental operation, that you just take a graph. If there are two non-adjacent vertices and you are adding one edge, whether you are getting another Laplacian integral graph. So this way one can construct Laplacian integral graphs from the known ones by just adding one edge. So this construction was completed by Iclaa. He characterized all constructively Laplacian integral graphs. That means the class of graphs and the condition for which you can add the edge, so that the new graph constructed will have also integer eigenvalues. So then if I consider, like, let's say graphs with Laplacian integer eigenvalues, but I'll put the condition that all the eigenvalues will be different integers. So they are distinct numbers. So the Laplacian eigenvalues, they can be 0, and then they can go up to n. So you have n+1 numbers to have the eigenvalues, but you need n eigenvalues. So one number can be left, and the other numbers can be thought as the eigenvalues. So that was the thing considered. So S is one n tuple of non-negative integers. Then S is said to be realizable by one integer matrix if S is the spectrum for that matrix. So the set of eigenvalues. So they consider it 0, 1 to n, and now take a subset of this such that it has n elements. And then the question was, we say that S is Laplacian realizable if there is a graph G on n vertices whose Laplacian spectrum is S. So the question was, if I just consider one subset where I is missing, so I'm taking n numbers. So does there exist a graph for which this will be the Laplacian? So the answer is positive. So you have such graphs, like for K2. If I look at, then K2 has the eigenvalue 0 and 2. So it's a with two vertices, and your 1 is missing here. So 0 and 2 are the eigenvalues, and they are the distinct eigenvalues. Similarly, for three vertices, P3 is the graph where 0, 1, 3, and here 2 is missing. And they have also four vertices graph. This is with 5 vertices. This is also with 5 vertices. In all the graphs, you can observe that one number is missing, but missing number is not the largest one. So n is not missing. Number of vertices, if you see, first one is 2, but 2 is there. Similarly, the second one, number of vertices is 3, and that 3 is there. So those graphs are constructed where I is missing, but I is in between 1 to n minus 1. So they gave this construction and they proved that for any I not equal to n, SIN is Laplacian realizable. That means there are graphs. So the graphs are constructed using join and union operation and successively. So if I consider S n minus 1 n, that means n minus 1 is missing. Then G will realize S n minus 1 n if and only if G is formed in the following two ways. So one is G can be constructed from G1, where G1 is realizing H2 n minus 3. And the second one is constructed from H, where H is the graph realizing S n minus 2 n minus 2. So they are sequentially constructed. And for any I between 2 to n minus 2, similarly it has been done. So they observe that for every n, such graphs are existing. But as I told, the last number is present. So then they pose the conjecture. If we take S and n, that means you are taking the eigenvalue 0 to n minus 1. Such graphs doesn't exist. So they pose this conjecture. S and n is not Laplacian realizable for n greater than equal to 2. Also, the second conjecture then was posed that for other i's, the graph which has been constructed is a unique graph. And the second conjecture can be proved easily if the first conjecture is proved, because the construction is done based on those graphs. So this conjecture was proposed in 2005 and it's still open. The progress was done in that same paper. They had proved that the conjecture holds for n less than equal to 11. Later Neumann, he proved that for large number, like if n is greater than equal to this number, then the conjecture holds. That they proved computationally. But because it's a very large number, so it's not concluding the result. Check the differential. Power is there.
So this kind of integer eigenvalue, these are the any relations with integral polyhedra?
No, I have not checked.
And what kind of application do you have?
Now integral graphs are getting. It is Laplacian integral graphs or adjacency integral graphs now they're using in the quantum information.
So all are coming from the practical motivation.
Practical also like because integers it's also mathematically bound.
What are the conditions to be imposed that so that all research commitment also will be
I have not checked in that. It's a strong condition.
This is an all that has mostly by knowledge. So there I'm just asking.
Rows and columns and the years to give the class of matrix and column must be the sum. That is the matrix zero lines from the tree. Each each and not each column rows but the young. And then that would be there when it's the matrix. Here Laplacian matrices are those kind of matrices, some columns of zero. That's why I consider it. But there would be because stochastic matrices, if you see rows and columns of the row for application.
So you are looking for application for statistics.
No, I have different matrices. That's what she talked about the zero sum.
She is asking whether diagonally.
And my question was, are there classes where you sum up the diagonal, not the rows or?
For the any class,
Yeah.
graphs, any class of graphs.
Yeah. In the case is the condition on the diagonal, the comes from K. And
Also not one.
What went wrong?
I think so the electrical signal broken down at the moment. This is sometimes
The need of everything.
and that since everything is connected, just takes time.
What sort of speed?
Positive and negative.
Okay. So the progress here on the conjecture is it can be observed that if SNN is Laplacian realizable, that means if there is a graph with eigenvalue 0 to n minus 1, n cannot be a prime number. Similarly, n is congruent to 0 or 1 mod 4. So these are the things, and the degrees will lie between 2 to n minus 3. Okay, so the largest degree will be n minus 3 and the smallest degree is 2. So there cannot be pendant. And SNN is Laplacian realizable, that this is like better and the class is now restricted. That G and G complement, they will have diameter 3. Okay, so if such graph exists, then it will have diameter 3. So now it's to show the conjecture, basically one has to look for the diameter 3 graph. So here I'm going to tell about G join. So G join is generalized join. So you take a graph and then take G1 to Gn if n vertices are there in G. So take G1 to Gn, and then if like I and J are adjacent, then put edges between the vertices of Gi to J. So this is also called vertex multiplication when your Gi's are isolated. So K Si complement. In that case, it's vertex multiplication. So in that case, I'll denote it as G, S1, S2, Sn. So when G1, G2, Gn, they are just empty graphs with vertices on. So this is a well-known operation, and if we consider a partition of the vertex set V1 to Vk, and it is called an equitable partition if like I take a vertex V from Vi, and how many edges it's getting adjacent, that will be same like with other like Vj the another partition. Then if I choose any I, how many vertices it will be adjacent, that will same for every Vi in the that Vi part. So that way it is defined. So the neighbors are same, basically number of neighbors. So the quotient matrix or the quotient graph is defined where the vertices has to be taken as the partitions. Okay, and like you have to get a multi diagram here. So you will the Vi from Vi to Vj, you will put the edges. Bij number of edges, and those are the directed edges. So this is the quotient graph, that way we can define. So given a graph, you can have a equitable partition, and respectively you can define a quotient graph. That's a multi-diagram. So this was proved by Cardoso and others, and that if you have a graph, and let's say S1 to Sn are positive integers. So if I consider the graph GS1 to Sn, then the Laplacian spectrum can be described in this way, that Di, where Di is this sum, the Di will be one eigenvalue with multiplicity Si minus 1 for I equal to 1 to n. And the other eigenvalues are the eigenvalues of this matrix C delta. So those means are not described explicitly, but they can be obtained from this matrix. So now if I define another matrix that is L G tilde, I am denoting S1 to Sn. Here I have put the entries accordingly, but you can observe that here the C tilde was like this. From here we have made this matrix, and I am taking the entries in this way. One can observe that this matrix is nothing but this is the quotient matrix of the graph G S1 S2 Sn. So that way they are related. And one can also observe that if I take the matrix C delta that we obtain, that matrix and this newly defined matrix, they have the same spectrum. They are similar matrices. So this is related to one graph because that matrix was just a matrix, and here I related it to quotient matrix of a graph so that we can look for the other eigenvalue. Then one can say that if G and H are two graphs on n and m vertices, and let's say I'm taking two n tuple, one n tuple and one m tuple of positive integers, then if S1, S2 all are same and those are equal to S, then G is Laplacian integral if and only if this new graph G S is Laplacian integral. This is the vertex multiplication. And if these two G S1 to Sn and H T1 to Tn, they are two Laplacian integrals, then if I take G join H and do the vertex multiplication with these numbers, that will be also Laplacian. Then this is considering the degree sequence. Let us take the degree sequence D1 to Dn of a graph, or you can take any non-negative numbers D1 to Dn. And they are arranged, D1 is the bigger and Dn is the smaller. Then the conjugate sequence is defined in this way, that it's D1 star to D, like it will continue infinitely, many terms you can calculate. after certain term it will be all will be 0. So dj star is defined as the number of di's which are greater than equal to j. So this is known as the conjugate sequence of the original sequence. So one can also remember that threshold graph. Threshold graphs are constructed in a way that you start with a isolated vertex, and then you can take another and make a join. You can take another isolated vertex and make union, that is again threshold, and then make a join, that is again threshold. That way those are constructed. Those are Laplacian integral graphs. Okay, and if you were taking a connected Laplacian integral graph and a connected threshold graph, then it has a dominating vertex because your last operation is the join. And Meris had given this result that's characterizing threshold graphs in terms of the conjugate sequence of the degree sequence. So he proved that G will be threshold graph if and only if the Laplacian spectrum of G is nothing but the conjugate sequence of the degrees. Okay. So this was the result. So using this, he proved that threshold graphs are uniquely determined by the spectrum. So if you are taking a threshold graph, what will be the eigenvalues? They are taken by only that graph. So there is no other co-spectral pair. So here we consider it in this way, that we have a graph G and vertices B1 to Vn. So we have degrees D1 to Dn. I'm taking a tuple H1 to Sn, all are positive or non-negative numbers also you can choose. And then I make a sequence taking H1 D1s, H2 D2s and Sn Dns. Okay. Now I'll define my conjugate sequence. Okay. Remember that conjugate sequence, first term is D1 is how many D1 star is how many DIs are there which are greater than equal to 1. Like this is defined. So I define the D star from that sequence. So now D is changed and this is the sequence. So then you can see that if G has a dominating vertex and H1 is not equal to 0, then these conjugates, they all are positive integers. And D1 star is nothing but H1 plus H2 to Sn, and Dn star is 0. Now using that, we gave another if and only condition for a graph to be threshold using the quotient matrix. So let G be a connected graph and D1 to Dn are in the degree sequence, and I constructed D in this way. G will be threshold graph if and only if D star, that is the conjugate sequence of D, that is realizable by the quotient matrix. So then this can be proved that if G is a threshold graph, then if we go for the vertex multiplication graph, that will be Laplacian integral. And if G1, G2, Gn all are Laplacian integral graphs, then if I take the G join of them, that will also be Laplacian integral. So then one graph is defined, that is anti-regular graph. So as we know, if we are having a connected graph, or it works also for disconnected, that at least 2 degrees will be equal. Okay. So we can allow n minus 1 degrees. So a graph is anti-regular if vertex degrees take n minus 1 different values. So Meris he proved that up to isomorphism there is a unique connected anti-regular graph on n vertices, and its repeated vertex degrees the integer part of n multi. So a connected anti-regular graph we are denoting by an. It can be seen that if I take A1, that is nothing but K1, A2 is K2, and n plus 1 can be constructed from n minus 1. So the way they are constructed, they are threshold graph. So what we could prove is, if you are choosing numbers like 0 and lambda 2 to lambda n, those are all positive integers, and they are arranged in this way that lambda 2 is the smaller one and lambda n is the largest one. then there exists a n tuple of non-negative integers S1 to Sn such that this 0 lambda 2 to lambda n that is realizable by the quotient matrix of the antiregular. So then using this, we have like this, I'll describe through one example that I chose lambda as 0, 4, 5, 8, 9. The proof is done using Faro diagram. So here 5 integers I'm choosing. Those are S1, S2, S5 that will be calculated using like from lambda 2 to lambda n. So what we do is we have to put first the lambda 1 to lambda n. So here like 4, 5, 8, 9. I'll put the points 9 first for 9. So 9 points are first given and then 8 points like this. Now S1 I can like I'll look in the other way row wise. So S1 will be 4 because 4 such, and then S2 will be 1 because there is only one row with 3. And last one also S5 I'll take 1. But after half of n, like n by 2, which numbers are there, like S3 and S4, that I'll put its sum is 3. And I can choose any partition. Okay. So then you can have like one partition I have like taken here. So 2 and 1, but you can choose any. Here I took 3, like 4, 4, 4, 4, and 3, and then 2, 2, 2, and then 1. So that will be the degree sequence that we are making using our S1, S2, S3, S4, S5. Then the anti-regular graph, and it's it's the quotient matrix that will be real. That is realizing that those eigenvalues. So you can see the anti-regular graph. A corresponding like graph has been drawn, and it's a multi-diagram, and it has the spectrum 0, 4, 5, 8. So this then gives that the result that if you are taking an anti-regular graph on n vertices, and let's say S1, S2, Sn be n tuple of non-negative integers, if exactly one of this Sn by 2 or Sn by 2 plus 1 is 0, and Sk is 1 for all other case, then the n tuple 0, 1, 2, and minus 1 is realizable by the quotient matrix of the antiregular graph. So far, like the conjecture, as we are suspecting that's true, but obviously for these eigenvalues, there are multi-diagrams which are taking place. And second one is also interesting that you can construct a graph for which the eigenvalues 0, 2, 4 up to 2n minus 2, they will come out. So that is also taken by the quotient matrix of this antiregular. So here I'll
Any comment? Any comment or remark about this beautiful communication? Please.
You have considered integer matrix and trying to compute spectral values which are integers, right?
Eigenvalues, yeah.
Yeah, then see, we calculate eigenvalues by using that characteristic equation.
Yeah.
So if we know the roots of characteristic equation, from that can we conclude something about eigenvalues of integer matrix?
I did not get the answer, but
No, my
you are
question
saying-
is, can we connect the theory of polynomials to this spectral values of integer matrix? That's what my question.
Yes, for every matrix, the characteristic polynomial we have to look for, and we have to get the eigenvalues from the roots of the polynomial. So that is the way only. And sometimes for nice matrices, we look for first eigenvectors, and then we go for the eigenvalues. So that way we don't solve the polynomial. But for any matrix to get the eigenvalues, we have to solve the polynomial. So the problem of finding eigenvalues is still with the polynomial problem. But if you are asking in other way, like I have certain numbers and they will be eigenvalues for certain matrix, that problem, that's the inverse eigenvalue problem. And here somehow it's related.
MATLAB will do it. MATLAB.
Fine, thank you.
Just a quick comment. So you've used here, you've used like Ferris diagram. So is there any connection between this kind of a theory with integer partition?
Yeah, because when we are choosing our S1 to SL, those are basically depending on your lambda 1 to lambda n, which you have chosen. And that way, like because I have related here to conjugate, so somehow we got the idea that we can use the Ferro diagram to do that. But as I told, that construction is not unique because for the middle ones, I'm choosing a partition. So any two numbers I can choose, like S3 and S4, I chose any two numbers. So that construction is not unique. So for given those numbers, you can have more than one multi-diagram.
Thank you.
Any other question, comment? Okay, so just a moment before to conclude the session.
I request Lina ma'am to do the honor.
And the session is over, so we can go for lunch. Thank you.
Thank you, ma'am. I have a small announcement. Now we'll break for lunch. So bus is waiting down. The next session will begin at 2:15 with invited talk by Sivaramakrishnan sir. So I request all the participants to be kindly on time. 2:15. 2:15. Thank you.
That is matching. Your dress. The color is matching, no?
Yeah.
You